Here we go. All right. So let's say that we have a speck of dust, okay? So we'll call it our little speck of dust. So our speck of dust is going to become our nuclei. So that's our solid particle suspended. So it's got our surface area so that our water vapor can attach to it. Yay, that's good. And then once you start condensing water vapor onto that, it becomes comparably larger than the other droplets as well. And here's the important part. It starts to allow for additional growth, okay? So this nuclei is essential for cloud formation. If you don't have that, you're not going to have any cloud cover. Now here's an interesting thing interesting question. Why is it, because obviously we have plenty of particulates out in the sky here in downtown Houston, don't we, right? What do we call those? Pollution. Right, smog, pollution, right? We got plenty. So why can't we form clouds every single day? Why, if we've got a big high pressure center there, I can't form any clouds? I got plenty of nuclei. Why not? What's missing? From? Right. There's no moisture, right? So if we don't have any, so that's the flip side of this, is I've got to have something that the moisture can hold on to, but I also have to have the moisture. If I don't have that, I got no cloud, right? So here we go. Plenty of sources for that. Wind erosion, soil, forest fires, that's the silicate, you know, that's, or even a piece of ash. Ash is fairly dense. It just kind of floats around. That can be used. You ever heard of the term cloud seeding? Have you ever heard that? Cloud seeding? Okay. Cloud seeding, what they tried to do back in the, I want to say it was like the 1930s, right when they got close to the Dust Bowl, you know, it was abnormally dry across much of the central plains and the southern plains here as well, even in the state of Texas. And so they devised a plan and they said, okay, well, what if they knew how this worked. They knew this was kind of the idea that if you're going to have clouds, you got to have something for the rain droplets to form on. So they said, well, what if we seed the clouds, so to speak? Basically, what if we create more things in the clouds for moisture to trap onto so that it will start to form more and more bigger, thicker clouds and thus lead to some rainfall, which is what the Central Plains needed so bad. Problem with that was, as we just discovered, if you don't have the moisture in place, it doesn't matter how much seeds you put into the cloud. If you don't have enough moisture, you're not going to be able to create any rain. So that's the other key and important parts of this. You've got to have it. Okay. All right. Start there. Let's start. Cooling. Yeah, let's start with that. Okay. So, two different ways that we can do this cloud formation. We can either do it in what's called a homogeneous nucleation or a heterogeneous nucleation. Okay? So the formation of this little ice embryos, which is basically what all clouds sort of start as, and then they melt to some degree, refreeze to some degree, depending on where they're located in the sky. So the idea here is that if you continue to create more colder air around, it creates more of a nucleation effect, meaning that you can get these water droplets bigger and bigger and bigger as they start to move. Okay? Now the other part to that is that a cloud droplet can cool as low, and this is really kind of interesting too. So a cloud droplet itself can continue to cool down to the point where it can get about 38 degrees below zero. Because that's a great question. I've had students ask me that before, and they say, well, it's fairly cold as you get up into the sky, so why don't all the clouds freeze, right? Like if you're flying on a jet and you're at 33,000 feet, if you've ever seen, they have the little, you know, this is where we're located, this is how fast the plane is going, here's the outside temperature. If you look at the outside temperature, sometimes it's like 35 below zero. And you see these big clouds and you think, well, how are these clouds just not ice at this point, right? Because 32 degrees is the freezing point of water. You say, well, how does that happen? Two different ways. One, if there's no foreign particles acting in or around that nucleus present, that cloud droplet can cool to an unusually low amount without freezing. part of that is because water vapor in and of itself doesn't necessarily freeze. It takes an enormous amount of energy for it to go from a vapor straight to a solid. Okay? And so the amount of energy that's needed for that isn't necessarily there to cool a cloud of that size. Clouds are a lot bigger than what we think they are. Yes?
Is that like the reverse or opposite idea of like having, like if you put crushed ice in a cup,
Yeah.
it's gonna cool your drink faster because there's more surface area?
Right,
So
yeah.
Like the reverse,
Yeah.
more surface area, so it
takes more energy to be able to do that. Yeah, exactly. That's a great example. Yeah, that's why same thing if you want to cool down, soda cans, brewskis, whatever, put them in a cooler, put in crushed ice, and then put in some rock salt. Because the salt itself serves as a sort of as a basically a condensation nuclei, because the salt molecules in there are bigger than the water vapor that's created off as it starts to cool, and it sort of serves as like a super freeze effect.
Right.
Learned that in Mississippi when I went there for school, because it was a dry county, and so everybody would go to the next county. You couldn't buy cold beer, by the way. You could buy it warm. You couldn't buy cold. The whole reason is that if you bought it cold, they were like, you're gonna drink it on the way home and you're gonna wreck and kill somebody. So you had to buy it warm. So everybody would just keep coolers in their truck with rock salt and crushed ice, and just, and then they'd still drink it on the way home. So that was effective. Oh, Mississippi, strange place. All right, heterogeneous nucleation. So if a supercooled droplet contains or contacts foreign particles that are in, the cloud droplet will freeze at temperature below freezing, but well above the Schaefer point. Schaefer point there is at 38.2. All right, why are we learning all this? Well, basically what we're learning with this is the idea that these clouds have nuclei that they have to form onto, okay? So you gotta have something to attach it. Two, that you can create a cloud still at very, very cold temperatures and not necessarily freeze that cloud out. And so that's why when you look in the sky and you say, okay, well, I know it's really cold up there, but it's still a cloud. It's not frozen ice raining down on my head. Why is that? It's the idea that water vapor takes an enormous amount of energy for it to cool. Okay. So let's learn about clouds. Does everybody understand that idea? So you just got to have something for that water vapor to form on. Some of that gets into the weeds. I just want you to understand the idea that you got to have a nuclei there in order to make that form. Okay. So now, the way we classify clouds is we do it by appearance and elevation. All right? Two most important things. Where's the cloud in the sky? What does it look like? So, clouds in particular, you're going to notice that there are three prefixes, I think is what they call them, to the clouds. And those will give you an indication of what category it's in. Okay? Here's what they are. Siri, strato, or strata, cumulo. Okay? So any cloud that we talk about from this point forward is going to have one of these three beginnings to it. All right? So where are they? I'm glad you asked that question. And so the way they look, a cirro-form cloud is going to be very wispy or look like little fibers in the sky. Okay? So a cirrocloud, let's do this. Cirrocloud's going to look like this. Something like that. Okay? So these clouds are really high up in the sky. Okay? These are your high altitude clouds. Next slide will show like where they are and all that. So your stratiform clouds are your more layered clouds. Okay? What I like to think of these, a good way to remember these, is I call these are our blanket clouds. Okay? That's sort of the way I've always remembered stratiform clouds. They're just blanket clouds. All right? So they, bless you,
Thank you.
they're going to look more like this. Okay? So it's going to create sort of like this little blanket layer. They're usually not very tall, but they're a little thicker than our cirrus clouds. Okay? These are a little lower in the sky. And now the one that everybody probably is familiar with, because we see it here basically every day, is the cumulus clouds, right? So our cumuliform clouds are heaped or puffy. What I always remember these are our popcorn clouds, or cauliflower if you're a health nut. Go for it. When did cauliflower become like the in thing to eat? Anybody know?
Only like 3 years ago.
Is that really? I mean, is it really that good?
No.
No, I don't like it either.
Someone tried me.
No, I don't like it. I'm a Brussels sprout guy. I love Brussels sprouts, which is weird because most people think they're, tool of the devil. But I think they're good. But yeah, cauliflower. Just, I don't get it. I was at dinner last night and somebody was eating cauliflower with like raisins. I'm like, what? Ew, no. Like street tacos. That's what I want. I want cauliflower and raisins. Anyway. So cumuliform clouds are heaped or puffy clouds. So these are lowest ones in the sky, which is the ones that we generally see when things get a little aggressive around here. These are what turn into our thunderstorm clouds.
Like the ones that are right now.
Uh-huh. Notice it's getting a little darker out there, isn't it? Let's see. What's our temperature outside, by the way? Of course it's shut off. So. Okay. So our cumulo clouds look like this. Okay? These are going to be our little popcorn puffy clouds. So, the altitude of the cloud base affects the temperature of the cloud and its composition. What do I mean by that? Well, meaning that the further that cloud up is in the sky, you think it's going to be warmer or colder? Oh, y'all better get this right, because this was one of the questions on the test. Colder, right, yeah. So as you go up, obviously the temperature goes down, right? Now, if the temperature goes down and we get colder, are we going to be able to put more moisture into that cold environment or less? Let's think about that for a second again. If I've got my little air parcel, okay, and this air parcel is at 70 degrees, and this air parcel is at 40 degrees, which one has more space to put water vapor in? 70, right? Because it's bigger. Warm air expands. It's got a little more opportunity to create some more moisture with it. Colder it is, the less we can. So we go from basically, and this is relative, warm, not as warm, ice cold. So you see, as we go higher into the sky, the clouds get smaller and smaller and thinner and thinner and thinner. So that's why your cirrus clouds always are super wispy, because they are made of almost entirely ice crystals. If you ever look in the sky and you see like a little, it's not a rainbow, but it's like a little prism. If you've ever looked up on a day where there's like we'll probably get some late this week when things start to clear out. But if you ever look up in the sky and you see some of these little wispy cirrus clouds and you can just kind of see some colors up there and it's a little wispy, that's what's happening, is that the sunlight is refracting off of the ice, right? Just like if you take a flashlight and you put it underwater, what happens? It splits the light, right? because the water's more dense, and so it refracts that energy as it moves through. So that's why the clouds change as we go up in height. Okay, so now that we got that, let's talk about where they are. Whoops, I made a mess. So your high clouds are your cirrus, your cirrostratus, and your cirrocumulus. Notice that we are now still using the prefix Cirri, right? So we know it's a high cloud, but within those high clouds, we can actually see different formations that include some of the other types of clouds as well. This is where it gets a little complicated. So it's not just as simple as like, okay, well, that's just a thin cloud, that's wispy, that's a cirrus cloud. Well, that could be a cirrostratus cloud, right? So what you have to do is you have to take the beginning part of that cloud and you have to go, okay, based on the beginning of that, where do I know it is? Cirri. Oh, okay, that's going to be way up high, right? Now, what type of cloud is that based on the amount of moisture that's in it? Well, it kind of looks like it's a thin little cloud deck. Okay, so that's a Cirri, that's a cirrostratus cloud, right? So, same thing with the middle clouds. These are anywhere from about 2,000, 5,000 meters, so what, 3.5 to 7,000, 8,000 feet? Altostratus, altocumulus clouds. And then, of course, our low clouds are going to be our stratus, stratocumulus, and our nimbostratus. Now, anytime, here's a little hint too, anytime the word nimbo is included in a cloud, that means rain. So a nimbo cloud, or anything that has the word nimbo in it, means that that is a rain-producing cloud. Okay? So for example, if we have a nimbostratus or a cumulonimbus cloud, if you were to see both of those clouds, you would go, oh, that means there is probably rain coming. Okay? So for example, today, if we look out here, we will probably not see a lot of cumulonimbus clouds, which is the big thunderstorm clouds that get super, super big. But, what we got going on there? Oh yeah. So that right there, ladies and germs, is basically a stratus deck. Okay? And you notice that there's really no start and finish to it, right? It's just kind of there. It just kind of goes everywhere. So you've got a relatively squat cloud. It's not super high, but it just kind of extends all over. Now, eventually what we'll get with that is we'll see some rain starting to form out of that cloud. So as soon as rain starts to form and rain starts falling out of that cloud, it goes from, let's say, a stratocumulus to a nimbostratus. So as soon as we get rain forming in that cloud, we change the name of that cloud. That becomes a nimbostratus cloud. Okay? So anytime you see the word nimbo in these clouds, that means it's a rain cloud. And then obviously the rest of that cloud name is just based on its height. Where is it? Is it a low cloud? Is it a cumulonimbus, meaning it's a cloud of vertical development? It is a cirrocumulus. Okay, it's way up in the atmosphere. All right. So there's all kinds of other types of clouds as well. You can have, or little characteristics, I should say, that they attach to that. You can have congestus cloud. Now notice that all of this is basically Greek too. That's where a lot of this prefixes come from. Congestus clouds, where they're crowded up into heaps. So like if these cumulus clouds are all kind of smashed into each other, which we'll see some days. Incus, which is an anvil shape. Those are on the top of cumulonimbus clouds, so big thunderstorm clouds. If you ever see sometimes We actually had one last week. I don't remember what day it was, but it was beautiful. I'm such a nerd. It really was beautiful. As I was driving home, we had this huge cumulonimbus clouds, massive thunderstorm cloud. I want to say it was out on the west side, out near Katy. And it got to the top of the stratosphere. It hits that cap, and so then it starts just going horizontal, and that's called the anvil. So like a big thunderstorm will look like this. So it'll start here, it'll go up, and then it hits the top of the stratosphere, and it can't necessarily really go any further, because where's all the weather trapped, right? By the way, everybody got that question right. Yay. What layer of the atmosphere is all weather? Right, the troposphere. Very good. Awesome. I know you guys all got that right. I love it. So it goes here. So as this builds, instead of this shooting up, it sort of goes like this. And kind of builds laterally. So it creates this little anvil shape out top there. Now, interestingly enough, this is where, and I saw this Saturday night on the radar, as I was stuck at work because that cold front got stuck up in College Station, and it dumped like 8 inches of rain in about 3 miles, and it wouldn't move. And it kept me there till about 1 in the morning, which was not fun. But what can happen sometimes is the lightning that's in here, your positive and negative ions, which we'll learn about lightning in a couple weeks. By the way, lightning's my absolute favorite. I'm fascinated by it. It's fascinating. 1, because we don't really know much about it. 2, it's pretty much the most powerful thing on the planet, and we don't know squat about it. Like, we don't even know where it's going to form or where it's going to hit. You just hope it doesn't hit you, because if it does, you're no longer here. Like all those people that are like, I've been hit by 10 times by lightning. No, you haven't. You've been hit by feeder bands, right? Little leaders, which is basically like putting your finger in a socket, but a lot stronger. If you're hit by a direct bolt, you're not here anymore. Like, it's just, no. But anyway, so sometimes the thunderstorm may be here, and this is, let's say, 5-6 miles out ahead of the storm. You can get lightning strikes that are 4 miles away from the actual storm itself. And that's where we always tell people that if you can see it in the distance or you can hear it, get inside. Because these bolts can get out there ahead. I saw it on the radar Saturday night. There was one it was at Bryan College Station, right in Brazos County there. And then just south of there, moving down towards like central Grimes County, let's say near Navasota, 4 or 5 strikes. Not even close to where the storm was. Can you imagine you're just like sitting there barbecuing, putting some brisket on, and also it's just like, pow! You're like, what? Seen it happen. It's crazy. Anyway, so mammatus clouds, which are super cool, happens after we get like big severe weather coming through. It's like kind of those low-hanging clouds that almost look like somebody took an egg carton and turned it upside down. They just kind of hang real low, and that's just the colder air that's sinking and it's trying to stabilize itself. So lenticular clouds, which are ones that you get on top of mountains that look like little UFOs that are up there. Obviously, we don't have any mountains here in the States, so we can't see them, but you get them out west all the time. Okay, so let's talk about what they look like. So stratus clouds, high clouds. Uh-oh, I have to move all this. And I'm going to blow through this pretty quickly because this is mainly visual, and you guys have this in your blackboard, so you don't need to stare at it every single time. You know, smart cookies in here. So high clouds are your cirrus clouds, your cirrostratus clouds, and your cirrocumulus clouds. Cirrostratus clouds, we've probably got some of those going on outside right now. Hard to tell though because it's starting to thicken up, so they kind of get obscured by some of the lower ones. But the bases are above 16,000 feet. Average temperature typically below 25 degrees Celsius, which is about 15 degrees Fahrenheit. So obviously, these are what? Frozen clouds, right? So they're made of ice crystals, which is why they're so thin. One of the reasons why you can't put a lot of moisture in these high clouds is because they're so cold. The cold, dense air can't hold, just like that little example. If we've got our little air parcel and it's only this big, it's not going to be able to hold that much moisture versus one that's that big. So these are always your little wispy clouds, probably the best way to describe them. All right, your middle clouds are your alto or your stratus clouds. So they can be altostratus, which is going to be more of that kind of blanket effect, which we'll see likely through the rest of this week, which is why we're not going to get a whole lot of sunshine. And then, of course, your altocumulus clouds. So they've got a little bit of that popcorn puffy look, but they're not very tall. They're just kind of flat, and it may look like, you know, like at Halloween here, when you take the you know, stuff you go to Spirit or the Halloween store and you buy that what spider web stuff they call, and it's just like cotton. You just kind of pull it apart. So there's a few breaks in it, but then it's thicker in some spots. That's kind of what the altocumulus clouds look like. Okay, so these are our middle clouds. And as we go down, we've got our low clouds. So our low clouds base start at the Earth's surface, which would be fog, up to about 6,000 feet. Average temperature is about 23 degrees. These include your stratocumulus stratus and your nimbostratus clouds. A nimbostratus means that it has what in it? Rain, right. It's a rain-producing cloud. So usually drizzle falls from the stratus clouds, which, once we get past today and tomorrow, a drop of rain chance is down to like 20-30% Wednesday, Thursday. I'll bet you that we probably see some, it's going to be one of those days where you're either walking around, you know, between classes here, or if you're driving back home or to work or wherever, and it's just kind of misting out there. Like, not enough that it's really raining, but enough that it's annoying, and you got to just kind of hit the wipers like once or twice. That's probably the type of weather we're going to see Wednesday, Thursday. So that's our low clouds. So obviously we go from the high clouds, what are mainly just ice crystals, to the low clouds, what are composed basically of entire water droplets. All right? All right, then our clouds having vertical development. These are our cumulus clouds. So we've got our regular cumulus clouds. These are sort of our little light, puffy cauliflower popcorn clouds. Our congestus clouds, we've seen these. These are when they start to get a little bigger. You get all kind of combined with them. And then, of course, our cumulonimbus clouds, which are our big thunderstorm clouds. These are the ones that really get massive in the sky. So they start off fairly small, but what happens, and one of the reasons why these have their own category, is because they create vertical development. So what you're getting is you're getting a little bit of rising air, which obviously is helping the clouds form, right? As the water vapor rises in the air, cools, condenses, turns into clouds. So as we get to more of an aggressive tone at this, we're creating more of an updraft, okay? So basically we're just pulling in more and more air to the point where we get to the cumulonimbus clouds, which is our big thunderstorm clouds. We're looking at this. So we've got this huge pull of air. That's why sometimes if you're outside and there's a thunderstorm that's formed and it's moving in your direction, if you're there, you can actually feel the wind being pulled against your body. That's the updraft. So like the wind is being sucked past you up into that storm. So it just gets stronger and stronger and stronger as these cumulus clouds get bigger and bigger and bigger. So here's one of these lenticular clouds, as we mentioned. So mountaintop, and it's a stationary, almost looks like a contact lens. It's probably a good way to describe it too. Thus the name lenticular cloud. So what happens is it's the middle atmosphere layer, middle layer clouds, and you've got really strong winds that are moving up above the mountain. Obviously, the mountains have to be high enough in order to have these. They're usually, I don't know, 10, 12, 14,000 feet, something like that. And so as the wind runs into the mountain, it slows it down. As it slows it down, it forces it up over top of the mountain like this. And so as it starts to slow down, congeal together, cools, condenses, and it creates these real thin little contact lens looking clouds over the top of the mountains. As I said, you see them out west all the time. They're kind of neat to look at. If you're ever flying and you happen to see one on top of a mountain, this little curve. The crazy thing is too, is normally they'd look a little closer like these little cumulus clouds here, but because the winds are so strong above the top of the mountain, it kind of serves as like a shaver, and it just kind of shaves off the top of that cloud, just makes it nice and smooth. So a couple of other unusual clouds that you can get what are called mountain wave clouds. And that's where you've got humid air above the surface, a little dry air down by the mountain. And then as it gets past the mountain, you create a little bit of a wave effect. And so what you're getting there is just the idea that as air is rising, it cools, condenses into a little bit of cloud cover, and then starts to fall, dries out, goes back up, because it heats up, cools, condenses, and so you'll get these little streaks of clouds that are past a mountain range. You see it a lot out like central Washington in the wintertime and some in the summer too when it's not too dry. But it's just really kind of neat. It's like right over the mountains, it's just dead dry, there's nothing there. And then as you get further east of that, in Washington and Idaho, for example, you get these little streaks, and they're almost like somebody made a layer of cloud, or a row of clouds. It's like a row, dry air, a row, dry air, row, a dry air. And it just boom, boom, boom. So they're kind of neat. Yeah, let's go. Save that for Wednesday. Okay. And we've got a couple of other specific types of clouds here as well. Noctilucent clouds form in the upper mesosphere above the altitude of about 50 miles. So these are way up there. You can only see them at high latitudes too. This is kind of the crazy part, is that these clouds are fairly rare, especially if you get further south in terms of latitude here. But these are up, in northern Canada, Alaska, for example. You can see these. And the key to formation is exceptionally low temperatures. So the ice clouds form at low water vapor pressures as well. So they can form from volcanic eruptions, chemical reactions, including methane, which is in the atmosphere. And so it's these here. So if you're watching or looking at this, the sun is way down near the horizon. So it's got to be either at like dusk. Usually at dusk is I think when you can see these. And so the area of the sky in the shadow is where you are, and then the area of sky in the sunlight is where we're seeing some of these clouds. But the key to this is these clouds are reflecting the sunlight. And so while you're standing in darkness, you can see these bright white like flashes in the sky. And it's these noctilucent clouds. So as I said, we're not going to see them down here in Texas. We're just too far south latitude-wise. But Alaska, you'll see that. This is kind of the same concept to how northern lights work as well. So, you've got the atmosphere, and then you have these chemicals and all of these, things just kind of running across the atmosphere and just flashing across the sky. All the solar radiation and the waves moving across. Which is why we can't see them down here, because the atmosphere is just too thick. All right. There isn't fog out there. So fog. Fog is an interesting cloud. It is a cloud that is in contact with the ground, right? We'll probably see some later this week too, I bet, because the dew points are going to be low, temperatures are going to be real low, and I bet we'll get some patchy fog in some spots. So fog, the reason we call fog is because it restricts visibility. So what we always look for in visibility is in terms of how far can you see ahead. And so when visibility starts to drop below a mile, that's when we start to see things like dense fog advisories come out from the National Weather Service. And it's just an indication that you're not going to be able to see that far ahead of you because you're literally driving through a cloud. All right. So it forms when the air becomes saturated through radiational cooling, convection cooling, if you throw a bunch of water vapor into the atmosphere that you're there, or expansional cooling. All right. So there's a couple of different ways we can do it. The most common that we see here across Southeast Texas is the idea of radiational fog. So radiational cooling causes the air near the ground to saturate, meaning that as we've warmed things up throughout the day, as we go into the evening and overnight hours, we slowly start to cool. And as we start to cool, we get closer and closer to the dew point. Remember, we know the dew point is what? The point at which the air saturates and becomes moist. So as we radiate that heat back into the atmosphere, we drop our air temperature. So let's say our dew point is here. So our air temperature starts to fall and it reaches that dew point. Well, if the air can't hold any more moisture, meaning that we can't hold any more water vapor, it's going to start to form a cloud, saturate. And so that's what fog happens when we get onto the ground. So it looks a lot like that. We don't get it as much in the downtown area just because there's a lot of airflow between the buildings and whatnot. But if you're, let's say, out in Brenham, Sealy, Fulshire, way up north, up near Conroe, even out in the Huntsville areas, or even out on the east side too, you can definitely get some fog. And we'll probably see some later this week. What's really cool sometimes is you'll get fog that'll form in these little valleys. So we've got this is New York State. So Syracuse is right about here, so to speak. And so you'll get this fog that fills up these little valleys. Where I used to live in Eugene, Oregon, it was in the bottom of what's called the Willamette Valley. It's a very large valley, you can see it from space. But it was notorious for getting fogged over because it was this fairly shallow valley, but it was pretty wide. And so it would cool, and it would get to the point where you would create this cloud cover that would get so thick, and that goes back to what I was saying, that you would have the overnight low would be like 39 degrees, and then the high for the next day would be like 41 degrees. And it's because we were just stuck under this fog deck, and it wouldn't move. In fact, let's see if there's any out there right now. Don't know that there is, but it's worth a look-see. Let's see if we can find it. Oh, fog, where are you? Hey, look, can anyone find the cold front? All right, right there. Look at that. Ready to play a little game? Let me turn this off real quick so you guys can see. Thank you. Can anyone tell me why that's not moving? This is a visual satellite, so we know we're looking at the actual picture, right? It's not temperature based, this is not water vapor based. What's happening here? Here's our front, right? Clearly, that's on the move. That's on the move. Why isn't any of this moving? What is that? Look at the very end. See how some of the clouds are moving, but that stuff in the middle isn't? What is that? It's a visual picture. What are you looking at? I'll give you a hint. It's cold. Hmm?
The high.
No.
Snow.
Bingo. It's snow. That cool? Look at that. That's all snow on the ground right now.
Oh, on the ground.
Uh-huh. Right, because remember, we're looking at a visual image, right? This is a visual picture of what's happening in the sky. So we've got our cold fronts extending here. Here comes some of our moisture coming in from the Pacific. And then we've got some of this cold air oozing south. This is what's going to continue to move throughout the next couple of days. And then all of that right there, that's all just snow on the ground. Okay, let me jump into Rachel here. Let's see if we can find a little fog. No, it's ain't there. you know what, Georgia might have some. Oh, there we go. Perfect. Okay. Look at that right there. Okay. This is we're really zoomed into Georgia. This is like northeast Georgia. That's South Carolina. Atlanta's like right there. Okay. So watch that spot. So as we go, here's now obviously it goes from nothing to that because why? The sun comes up, right? So we can now see. We can now use a visual sun. So watch that spot. Notice that you see the clouds are moving, right? But it's not really moving because that's fog. So as the sun comes up, watch what happens to that spot.
It disappears.
Yeah, kind of burns off, doesn't it? So what's happening is that fog gets trapped close to the surface, and it creates its own little cloud. But once the sun comes out, what happens? What's the sun do?
Evaporate.
Right, it heats up the ground, and so all of that moisture that's trapped there in that fog starts to heat up and eventually just evaporates into space. So you'll get that. There's too many valleys down there. Let's see if I can find one more. Oh, those are all trapped up there. Go darn it. Ooh, yeah, perfect. Same thing here. So all of this. Whoa. All of that right in there. So that's all fog. So the Appalachian mountain range runs like right here. And so what's probably happened is all of this air that was a little warmer yesterday kind of fell down into the valley, which is right around outside Charlotte here. Or actually, Charlotte's a little further. And so all of this, so you've got clouds moving through, but notice this stuff. And usually fog, when you look at it on a visual satellite, it's really gray. It's pretty dense. It doesn't have like these little cool little features that's moving. It's just stuck right there. So that's this morning, so watch that. This is going to be a little more stubborn to burn off. So notice that you see it kind of disappearing, right? Yeah. So that's the fog that eventually, as the sun comes up, kind of burns that off. So that's what we're looking at there is sort of a cloud on the ground. So that's our fog. Okay. So two other ways that we can get our fog. Radiational fog was what we were looking at right there. Radiational fog is basically just from the cooling of the night, cools down to the point where it forms these clouds, right? The other way that you can get fog, and we'll see this sometimes down around the coast, like southern Missouri County, Matagorda County, even down towards Galveston sometimes, is you can get what's called advection fog. This is what happens out in San Francisco. If you ever see pictures or video of San Francisco and the bay is completely blacked out, it's just fogged out, that's what's happening. It's advection fog. So the advecting air passes over a relatively cool surface, causing condensation. Okay, and then so what you get is as that air that is slightly warmer out over in the Pacific in the bay there, as it moves over the cooler land, it starts to cool, condense, and so that pushes it inland, and so you'll get the bay getting fogged out. If you've ever flown in or out of San Francisco, it is one of the most troubling and difficult airports to get in and out of, especially if you're flying early in the morning, because they have to either back the flights up or they'll shut the airport down for a couple hours because it's just fogged in and they can't do anything about it. And so of course that backs everything else up. It's trying to get west. But that's another way that we can see fog working its way through too. So you've got your different cloud types, your high cirrus clouds, your middle clouds, your alto clouds, your stratus clouds, your low clouds, which are your stratus and your cumulus clouds, and then the ones with vertical development, which is our big thunderstorm clouds. So what we're going to talk about on Wednesday is we're going to talk about precipitation and how does that form. Okay, because we've got the cloud, now we got to figure out how do we get that to fall out of the cloud, get things going from there. All right? Okay. I will have your second half of your exams back to you on Wednesday. The grades all recorded as well. And we'll be good to go from there. So far, as I said, you all did fine. I've got about 4 or 5 that I got to finish. All of them so far have been great. Everybody hit what you needed to, so that's wonderful. It makes me happy. Okay. That's what we got. I'll see you guys Wednesday.